Hi, I'm presenting OpenFlume, which is part of the research that I do as a research engineer for a fluid mechanics lab. And what I'm going to be talking about is this flow tank that we built and some of the motivation behind that, how we made it open source and why, and then also some of the nitty-gritty on the design and building acrylic tanks and things like that. So if you're interested in fabricating with acrylic, this is also a good talk for you. Before I start, here is some fun eye candy and goodies. So this is a cool acrylic and ball bearing toy. This is a tiny wind tunnel that you can hold in your hand and see vortices and vortex shedding. And then this is a little sample of one of the pieces of the tank to see like how the construction method works. And yeah. So some background on the research that my lab does. We're a fluid mechanics lab, and we study mostly small and intermediate scale fluids. And typically this is air-water interfaces or air-fluid interfaces. So things like droplets on water baths or droplets impacting a flat plate that's hydrophobic, bigger rigid impactors or compliant impactors in this case. And then what I'll be focusing on in this talk is the reason for this flow tank is flow past a sphere, which is in the bottom left photo. So for this project, the motivation was to try to understand drag at these intermediate scales. And it's pretty interesting, actually, that there isn't a lot of literature on what seems like a really fundamental kind of canonical problem. So for really small spheres, like think on the order of like dust on the surface of water or cells like in biotransport situations, there's a ton of literature. And those regimes are dominated by the viscosity and surface tension if it's on the surface, but not the inertia of the water, like the momentum doesn't really play into account. And then at very large scales, people have studied drag on spheres as a stand-in for something like a boat, where the boat hull you could kind of imagine as a sphere. And in those cases, surface tension doesn't matter at all, viscosity can be ignored in a lot of cases, and those are inertia dominated. But at these intermediate scales, both or all of those forces play into account, and they have roughly the same order of magnitude. So you can't cancel out any of those terms, and it means that it's an area that isn't well studied and where we can actually find some new interesting physics. So this talk is called OpenFlume. What is a flume? So if you ask a fluids researcher what is a flume, this is kind of the picture that they might have in their head. This is like a giant research grade infinity pool that you put things that you want to measure in, or they're used for like sediment transport, seeing how erosion happens in rivers. We work with a lab that has a flume, and they are studying the turbulence and vortex shedding on the whiskers of seals. So they put like 3D printed seal whiskers into flumes. There's all kinds of things that people want to do with flumes. And typically they're sort of this big. They're often, you know, hundreds of thousands to millions of dollars, and that's before you add in like instrumentation or like the operating costs are really high. And so this is a really significant facility. And it's not really well suited for what we need, which we need a uniform flow to measure drag, but like the ripples on the surface is probably bigger than the sphere that we're trying to measure in the first place. So we needed something smaller. And when we looked for small scale flumes, like desktop flumes, there are some available, but they're almost all made for education, as like demonstrations and things like that. So the type of thing that you might use in a college fluids lab to learn about, in this case, like the flow over a weir or sediment transport, like this sand moving across the weir. And these are roughly the right scale and size, and they even have the right flow rates, but they don't have the other type of characterization that we need to be confident that the flow is uniform, has low turbulence, and they're also really expensive. So these flumes that we looked at they're not really easy to modify because of how they're constructed. They're really, you know, they come with this kind of curriculum that you can use, and they're just not like research grade tools. They're really like education grade tools. And they're on the order of like $10,000. So this is not like a cheap thing that we're confident will work for our experiment, and so this is why we decided to build something from scratch. And so this is what we came up with in the end. This is OpenFlume. It's a fully characterized flume that you can download the files for, and we go through the whole build guide in the paper. It's digitally controlled with a commercially available, pretty cheap pump, and it's certified open source, and it's about an order of magnitude lower in cost as well. So as long as you don't count the many, many hours that it takes to build one, this is a great option in terms of cost. So before I get into how the flume works and how we built the flume, I just wanted to briefly go over like the research that came out of this. So after about a year of doing experiments on drag with the flume, we published a paper. Robert Hunt was the main, he was a postdoc that I worked with on the design and getting the experiment set up, and then he ran all these experiments, and we got some really interesting results. So this just kind of shows the setup. Excuse me, there's a sphere. It's on a load cell, and then we drop the sphere into the water and out of the water in a uniform flow. And then we compare those forces with different spheres and compare it with some theoretical and some numerical simulations. So what did we find? Turns out we found some really interesting things. So the free stream drag of a sphere is something that's like well known in literature, has been for a long time. And what that means is if I take my sphere and I put it all the way into the water, so it's fully submerged, it should have a certain amount of drag. And that's characterized by this 0.4 value for the drag coefficient. And this shows over a bunch of different flow rates that all of these experiments approach the same free stream, fully submerged drag. The thing that none of the theories that we looked at explain is this huge peak before we get there. So you might think that when the sphere is partially submerged, you have part of the drag. Like if it's half of the area, then you get half of the drag. And that's sort of what happens at some scales, but it turns out at this scale, it's not at all what happens. You get this huge peak that can be 3 or 4 times the free stream drag because of the deformation of the water, because of the wake and the way the water builds up in front of the object and adds this extra pressure onto the object. So this is something that wasn't documented or observed, and so this paper kind of showed this and also showed how whether the sphere is wetted or not matters a lot. So the shape of the drag and how much drag you experience is different going into the water when the sphere is dry versus coming out while it's wet. And then it's also strongly dependent on the surface. So on the right, we have a few different materials. So one is a acrylic sphere with a super hydrophobic coating. Oh, I don't know if I mentioned the spheres are 1 centimeter. So again, this is like canonical experiment, like slow flow rate 1 centimeter sphere. And then acrylic uncoated, and then a sphere made out of a super hydrophilic material, an agar. So this is the early version of the flume that we actually used to conduct these experiments. And we had this idea in mind of trying to keep it open source and make it reproducible. And so we chose acrylic, laser cut acrylic as the main building material, and thought that digital fabrication would make it easier to scale, easier for other people to reproduce. But it turns out there's a ton of problems with using laser cut acrylic with solvent welding to build these tanks. And that was something that we didn't really expect, and we learned the hard way, where for the entire lifetime of that experiment, we were constantly, adding a little silicone here, a little solvent there, to kind of build up a flume that would not be leaking constantly. So here's some examples of with like this long-term loading, the water's heavy, it's a big span, and these little cracks that form on the edges of the acrylic because of like heat stress put into the material during laser cutting slowly propagate over time. And this was just kind of a constant problem. So for the second version, we kind of started from scratch and tried to design something that other labs could hopefully use for a longer time, something that'd be more reliable, more stable, but still reproducible. And the big change with this was we actually moved away from digital fabrication to more traditional fabrication techniques. So the entire flume was built in a wood shop, not in our lab that has laser cutter. And we used much thicker acrylic, which again, it's really easy to use thick acrylic with woodworking tools. It might be hard to cut like 1/2-inch acrylic with your 35-watt laser, but a table saw doesn't care. And we added extra edges in a lot of the places to reinforce those areas that we had leaks in the original version. And also to support the weight of the water, we added an aluminum substructure so that there's just less overall loading on the acrylic itself. So here's some of the subsystems that are in the flume that are documented in the paper. But it's a pretty simple system. There's a big tank, and there's a lot of consideration into the shape of the tank and how we built it. And then there's a TNC that runs a pump with a PWM signal, and the pump that circulates the water around. So quick specs, like I mentioned, it's under $1,100, so roughly an order of magnitude cheaper than the other benchtop flumes. It has really good, like on par with best-in-class commercially available flumes at larger scales for the turbulence that we measured, and it's modular, it's open source. So back to the design methodology. We realized that in order to maintain the reproducibility of the flume, by restricting ourselves to a very small set of tools, it allows people all over the world to be able to have access to those tools and reproduce it with skills that are pretty universal. Like everywhere that I've been in the world has a wood shop somewhere in town. There's someone who knows how to run a saw, who understands like clamping and gluing, and we're basically building a piece of furniture just out of plastic instead of wood or plywood. But in order to get those woodworking tools to work with this material, you need to change the cutters. So in this case, this is a high tooth count and zero rake table saw blade, which kind of scrapes the plastic instead of cutting it like with wood, and leaves a really beautiful edge finish that you can just glue straight from there. If you haven't ever used acrylic specific drill bits to drill acrylic, it's unbelievable. You can just like drill press as hard as you can straight through a piece of acrylic, and it doesn't grab at the end. It just goes through, and it doesn't explode or tear out on the back. It's really cool. And then in terms of the fabrication method, all of the acrylic can be bonded with a solvent. So instead of gluing panels together with an adhesive that's another material, you just melt the acrylic surface and squish the plastic together, and then when the solvent evaporates out, you're left with a single monolithic part that's watertight and can be optically clear if you prepare your surface as well. So this and a router is kind of the whole toolkit that we used. In order to get some of the more complicated geometries we needed, we ended up using a pattern routing bit. So if you haven't seen this, it's a ball bearing that's the same diameter as the cutter, and you stick this in a table router, and then we just bandsawed to a line and sanded a piece of MDF that has the profile that we want, and then by running the bearing along the MDF, it transfers that shape to the acrylic. So we can get these precise, repeatable, very nice 90-degree angled cuts in acrylic, again, without using any digital fabrication tools. And then for the fabrication, like assembly, again, it's just traditional woodworking type equipment. It's clamps and, you know, some basic jigs and things to help keep everything aligned. So we had access to a certain thickness of material, but one of the reasons that we wanted to, or one of the things that we wanted to maintain with this project was the editability. So we used a parametric CAD software, and here you can see that you can just change the thickness of the walls and the whole model updates. So if your lab needs a flume and you need it to be thicker walled, maybe this would accommodate that. But we had a lot of back and forth about what CAD software to use, which I don't want to go into, but I think that's a really big need in the open hardware community, is like open source CAD tools that are parametric and are good. So back to the pump. We sourced a BMW coolant pump. BMW makes cars that they don't belt the coolant pump to the engine like everybody else because they want higher coolant rates at lower RPMs than would otherwise be possible. But it turns out there's a bunch of really cheap third-party replacements for these, and you could even just get a pump out of a car. So this was another way where we kept cost low and availability, like global availability, high. By just choosing the right parts. And we had to go through some validation and things to make sure that this pump would work, but it ended up working really well. Similarly with the flow sensor, it's like a cheap flow sensor people use to measure how much water they're using in their gardens and things like that. And we don't use this for quantitative measurement, but more to see if there's like drift day to day, things like that. But it's been a useful tool. So the build documentation for this project ended up being probably the biggest thing that I've learned. Starting with build docs from the beginning of a project like this is really important because there's just so many little tips and tricks and ideas you have and setups that you make along the way that when you're trying to, kind of go through your photos and forensically reconstruct exactly what order you did things after the fact, it's really difficult. So I think that good build documentation is super crucial for successful open hardware projects, and also the most time-consuming and most difficult part of the whole project, and something that I'm definitely still learning. But one of the best tools to producing these build guides and build docs was the CAD files themselves. So things like programmatically naming the parts that go into the assemblies and then carrying those names through the documentation, the CAD, the cut sheets, makes it a bit more legible. And then I think it's also useful to have photos of the real things so that you can connect the CAD to reality. So here's an example of one of the ways that the CAD software can be used to generate really useful build docs, where in this case, there's a specific order that you need to assemble these parts and specific ways that you use the jigs. And it's pretty difficult to capture that in words, but really trivial to understand the order and why you use the jig and how with a short animation that's generated in Fusion. So this is the constriction, the outlet tank. I'm going to skip that. And the need to do good documentation is difficult because of how many things there are to document. So not only do you have to document the process and how you use the tools or how you do the solvent welding, how you clamp it, the order, but also the jigs that we use and how you build the jigs to build the thing. It's a really big problem, and I think that I don't know, there's a need for more people to come up with good ways to streamline this whole process. But again, what we ended up doing was using the CAD models to kind of show how the jigs would be used. I don't want to go into this too much because I have some other fun things to show, but as part of the whole process, we did a bunch of kind of iterative testing on how to condition the flow to get a really nice uniform flow in the tank. And one of the fun things that we came up with was, instead of buying a commercially available honeycomb, which can be really expensive and difficult to source, we just super glued straws together, and it works great. It takes a little while, but I started masking taping straws into strips so that they don't all go everywhere, and just cut it with a ruler and glue it. And and that's how we got these really good results, was a 3D printed inlet diffuser, which is our one 3D printed part, and then some aquarium foam and flow straighteners made out of drinking straws. This project was kind of interesting because it's primarily a fabrication, DIY project, but there's still a hardware, embedded software component. And so in the past, the lab has done circuit boards for something like this, but we actually decided against that here because of the fact that the circuit was so simple. We thought it would be easier to just have someone build a basic little amplifier out of an op amp to drive the pump, instead of having to learn JLC sourcing if they've never done that. An engineering student at a different university probably has used a breadboard in a class, but probably has not used JLC. So thinking about the broader scientific community and not just the open hardware community drove a lot of the decisions behind how we designed this. And then for the characterization, we use an interesting technique called particle image velocimetry, or PIV. So if you're interested in this, I can talk about it, but we use lasers and cameras, and it's fun. So there was a recent paper published by Julian Sterling, who is the original designer of the OpenFlume microscope. It's one of the kind of crown jewel open source science hardware projects. with a really big global community and a lot of interesting projects that are based on it. But his paper is about why it's important to have the tools open source as well as the science open source. Like this idea of sharing knowledge is fundamental to science, but well, I'll just read it. Experimental science remains a key pillar of science in the digital age. The ability to physically test a theory or hypothesis must always be part of science. As such, the movement for open science cannot overlook the experiments themselves and the instruments that enable these experiments. For open science to truly thrive, we must support open sharing of experimental setups, including the full open description and any custom instrumentation. And I think what he goes on to in this paper to describe is that just sharing the CAD file doesn't mean making it an open source project. It needs the documentation and it needs the organization for it to actually be replicable. And that's something that very few projects in scientific papers are doing. Even if they're open, they just dump everything to a repository somewhere. They don't have this documentation. And it's a really big added effort, but it's the thing that determines whether or not the project will be successful. So thank you. This was OpenFlume, and I'll answer any questions about it, but then I also have some slides about building the fidget spinners with some practical tips and tricks. Questions? Thank you. Yeah.
Can you tell us about the laser camera thing?
Yeah. So I wish I had more slides about it, but particle image velocimetry, or PIV, is a really commonly used technique in fluids. And the way it works is you add tracer particles to the flow. So for us, these are about 10 microns, or like the size of a red blood cell, and they're these hollow glass spheres that are neutrally buoyant. So as far as I'm aware, they kind of just take a bunch of glass and like shoot it through a spray nozzle into water and then sort it by density, and then they sell it to you for a lot of money. But they're the same type of spheres that are put into like paint on the roads, like the hollow glass microspheres to make the paint glow.
Retroreflectors?
Yeah, exactly. We don't use them as retroreflectors, we just use them to scatter light. So the way the technique works is you take your laser, it's a pulsed laser, so you get a flash, not a continuous beam, and you spread the laser out with a sheet optic. So one way to do this is you can actually do a lot of fun stuff with a laser pointer and like a glass rod, and you can see all kinds of like smoke plus a laser pointer and a glass rod is a lot of fun. And that's the technique of PIV, is like you watch the particles move, and when you compare one image of the particles to the next image of the particles, you can do this kind of matching of different areas of the image. And the best match, you then draw a vector from where you started to where you ended up. You do that at a bunch of different grid squares. You can tune things like the size of the grid or how far you look, and you end up with the vector field of the flow. And this is specifically like one slice of the flow. So in order to get the full volumetric picture, you might need to do a bunch of slices, which is one limitation of this technique. But you can get quantitative, really accurate information. You can do some fun tricks to measure really high-speed flows, even with pretty like low-speed cameras. That's really interesting. But yeah, answer your question? Yeah.
Also, different laser related.
Yeah.
You mentioned that when you were using laser cutters for this, you faced a lot of problems with leaks and whatnot. I'm curious if there's any particular thing that you found made that process less useful than the saw.
Oh yeah, so that's true, I didn't mention that. So the heat affected zone from the laser is a huge one. It adds a bunch of stress that isn't often a problem, but once you add the solvent, it just immediately starts crazing and cracking. And so something about the solvent, like releasing stress in parts of this in the material, but I don't know. You'll take a piece of laser cut material and add like solvent to it, and then it just looks really bad after that. So that's one problem. The other problem is that you never get a perfectly 90-degree angle on the edges, and so when you go to bond this solvent is like thinner than water. It's really, really thin, and so you need good surface contact for it to wet under, dissolve the edges, and then get squished together and form a good bond. And I think that that's really what was the problem with our first version, was that there just wasn't enough surface contact in a lot of these edges. So we ended up having to, you can use a thickened acrylic solvent where they just like dissolve some acrylic in the solvent and it's all goopy to try to fill in those gaps, but it gets really messy, it's difficult. Or you can use like RTV silicone, which is what we ended up doing, to just fill in the gaps and slather over the problem. Yeah. If there's no other questions, I'll show you how to make fidget spinners. So the fidget spinners are fun because you can use the laser cutter because we're not actually bonding the edges. We're only bonding the surfaces. So if there is any crazing, it's not really a problem. But we start with these sheets that will laminate together. The top and bottom are 1/16 inch, and then the middle slice is 1/8 inch or 3mm acrylic. So one big tip when you're doing anything with acrylic is you want to leave the paper on as long as possible. So any surface that you're not going to need to glue on right now, leave the paper on, because you, especially with the solvents, you'll get defects on the surface from little drips getting everywhere. Like some solvent on your glove you'll end up like leaving a fingerprint. So that's one big tip. And then also making sure that you get a full, that the solvent will wet fully through the joint, and waiting a few seconds before you apply pressure. You really want it to soften the acrylic and get slippery before you then clamp it. If you don't do that, then well, for one thing, it's difficult to get it to fully wet through, and you'll often end up with air bubbles in your joints that can cause leaks. So we do the inner and outer rings and just aligning them visually, and then add this cylinder that gives you the flow past the cylinder visualization for this specific toy. And again, it's just tiny drop of solvent and then placing the cylinder in place. So one thing that I found was useful was after I flood the rings on the top, add the top layer, one thing that was useful was adding a little bit of solvent into the whole body of it and then just shaking it around everywhere. And that seemed to just kind of smooth things out. And like, I don't know, the vapor from the solvent maybe dissolves all of the edges just enough to make it more reliably watertight. To get the text, we used acrylic paint, which bonds great to acrylic plastic, and just push it into the grooves with a like stiff brush, and then wipe it off with a paper towel after. So that's a nice way to get like a high contrast lettering. And I used a vector font for this because it makes the cut file a lot faster. And then filling it is pretty fun. So the fluid inside is called rheoscopic fluid, but it's just mica powder in water with some food coloring. So simple stuff. The mica powder is these little flakes that orient to the fluid and show the flow in a really nice way, like play with the light. And to actually put it in, you need 2 holes. One is right here, and one above it acts as a vent. So you syringe in from really anywhere below the vent, and then it just fills and the air gets displaced, and kind of like you're bleeding a brake line or something. It's pretty easy to get a very small amount of air inside these little fidget spinners by having 2 holes. And then just dropping a little bit of laser cut acrylic over it and solvent welding it in place seals the whole thing off. Cool. Thank you. Check out our GitHub.